Okay. So I have started recording. And let's talk about latency. If we are talking about the latency involving hard drives, then it would come from many sources, several sources. So one is there is a rotational latency. I'll write latency over here so I don't have to keep repeating it. Then there is seek latency. There is transfer latency and settling latency. So who's at my feet? Hello, Fredo. You can't see everybody. Let's lift you up. Hello. Rub the belly. Okay, you go now. Up, up. Here, take a dog chew. Go away. Fredo. There, okay. All right, so rotational latency comes about because a spinning disk spins. And the location of the heads is fixed apart from going in and out, but the disk has to rotate around such that the data that you're looking for passes underneath the heads. And if you wanted data that was over here at this very instant, you'd have to wait until the disk spins all the way around. So that's rotational latency. And rotational latency is fairly small. The faster that a disk spins, the smaller it gets. And the popular drive speeds are 5,400, 7,200, and 10,000. I have also seen 3,600, but that's really rare as far as I know. Okay, so the faster it spins, the more expensive the drive. The second type of latency is seek latency, and that comes about because of the movement of the heads from track to track. Movement of the heads in and out. So here's the spindle, the head, which is the read and write mechanism, has to travel from the inner cylinders to the outer cylinders and back again. And that is on the order of milliseconds on average. So the rotational latency would be, let's say, 1 over 3,600 RPM. So it's measured in minutes. And you'd have to do the appropriate multiplication or division. But the seek latency is on the order of milliseconds. Now, track-to-track latency, seek latency, is very small. And that is track-to-track is a movement of one track. So the puppy must have told the other dogs that I had biscuits in here. Now they're all here. Now it turns out that track-to-track latency, seek latency, is so short that doing a sequential, a very, very large sequential read or write on a spinning disk can actually be faster than an SSD, especially for writes. And there's a reason for that that we haven't gone into yet.
So sequential read is sequential read?
Sequential what?
Sequential read compared to sequential read for both.
Well, for SSD, there's the notion of sequential is irrelevant because there's no moving parts. But a sequential operation on a moving disk can be faster than arbitrary operations on an SSD.
Is an SSD random access?
An SSD is random access.
I feel like it is then.
You feel like it isn't?
Yeah, because
Well,
if you're writing a bunch of small files or reading a bunch of small files, it takes a lot longer than writing one bigger file in an SSD, at least from experience.
okay, well, explain to me how a device with no moving parts would be slower to read from one spot than any other spot.
Well, I mean, there still has to be a transfer of information, so perhaps it's further away on the circuitry. I don't know. I just know that like if you do disk tests, the sequential read is significantly faster than random read on an SSD.
Okay. Well, what is significantly slower on an SSD is writing. And a sequential write will be faster on an SSD than a random access write. And the reason that writing is very slow, relatively slow on an SSD, comes about because of the way that the electronics cause the writing to take place. Okay, so with an SSD, which we have not covered, but an SSD, imagine if this is all of your space on an SSD, the SSD is going to be divided up into sections which are larger than blocks. So there's multiple blocks in each of these sections. And in order to write one bit in that section, the entire section must be erased. And then you can write your bit. So writing to an SSD is very slow, comparatively speaking. So if, for example, you wanted to write one bit, you would have to most likely copy the entire set, go through the time to initialize another block, it's not a block, it's another segment, copy everything into that newly initialized and write your bit. And then free this section. Okay, so writing to an SSD is fairly slow. But getting back to hard drives, the final, okay, so two very small sources of latency is the transfer latency, and that is the time that it takes to get from the hard drive to memory. That is going to be pretty small. It's, after all, SATA drives advertise 6 gigabytes per second in transfer speed. And then smallest of all, perhaps, is the settling time. And the settling latency, is because the disks are ballistic in nature. They start accelerating halfway to their destination. They start decelerating. And then when they arrive where they're going, they're not exactly perfectly positioned. There's going to be a little bit of noodling back and forth to make sure that it is now over the optimal place to read a particular track, read or write a particular track. So settling might be, if this is the head, the shiny bit's the head, settling might be, and then it's settled. Do you see it's a little settling, and then you're ready to go. Okay? Okie doke. Other questions?
Where can we find some of the presentations that you have, like the thing on floats or the thing on hard drives as of recent.
Well,
Like the
all of
PowerPoint,
all of
the
the
present
classes.
points, the PowerPoint presentations that you have or have shown in class.
Oh, I didn't even put those online, did I? I think maybe I did. Let me look. Because they're so minor, but let me look.
Looking
Let's
through
try.
the thing is a bit quicker than going through the video again.
Okay, well, let me see. Either if I did put it online. Okay, so the source code to the float program is on Schoology. Let's check GitHub. All right. The floating point PowerPoint is already on GitHub. So I'll show you where it is. It is here. Okay, does that do it for you, Thomas?
That it does. Thank you.
Good. Okay.
I was also asking because I remember you having like a presentation on disks, or was that just me
disks.
Imagining things?
Yeah, you're imagining things. I hope you imagined I was really good and articulate and funny. Okay, other questions?
I have a question. Can we review thrashing, please?
Okay. So let me switch screens. So based upon the requests that a disk must service, okay, this is after I'm done with disk thrashing, I'll go over some other uses of the same word with the same meaning, but in different places. Okay, so based upon the requests that a disk must service, thrashing is when it spends excessive or problematic excessive time seeking at the expense of reading and writing. So reading and writing, those are the productive parts, right? So the time that you spend getting there is in some sense wasted. It's wasted time. So if this were block 0 of your hard drive, and this is block N, where it's the maximum, it's the last block of your hard drive, it's possible to get lots of a request here, and then a request here, and then a request here, and a request here, and a request here, and a request here. So unfortunately, the disk heads are going to be doing this sort of thing. And the result is that you're spending a lot of your time seeking back and forth. So that's disk thrashing, where the requests, for whatever reason, are coming in such a way, in such an order, with the right kind of timing, that the disk head is going back and forth and back and forth and back and forth. Right. Okay.
So it's just that situation?
Yes.
Okay.
Yes. Now, there are other uses of the word thrashing in computer science, and one closely related area of computer science is operating systems. And then it is also possible to thrash in swapping. So swapping is the notion where you keep not all of a process's address space is kept in memory. And swapping is when you need a part of a process's address space that's not in memory. It has to be brought into memory. So that involves a disk I/O. Hopefully it's an SSD, maybe it's not. But in any case, it's going to cause a halt, to a pause to working on that, doing the work of that process, while a part of its address space is brought in from mass storage to main memory. So thrashing can happen in the following way. Let's make a contrived example of a computer that has 3 blocks of memory. Let's say 3 kilobytes of memory. Okay, so here's my 3 kilobytes. And suppose I need to access, so this is 1K, 1K, and 1K. So I access the first page. If the order of access were like this, the first 1K, the second 1K, and the third 1K. So now you have 0, 1, and 2 in memory. If the very next thing that you needed to do was in section 3 or block 3 of the address space, well, one of these will have to be thrown away. So let's say I throw away that one, and now I've got 3 here. The very next thing I want is, oh, darn, 0 again. Well, that means that one of these things is going to be thrown away. I need a smaller eraser. Okay, so now 0 is here. And then the very next thing that I want is, oh, that sucks. I want something from the block number 1 of the address space. Ah, damn it, it's not in memory, so I'm going to have to throw this away to bring in section 1. So what's happening here is thrashing, because we are spending a lot of our time just moving blocks of memory in and out based upon the order of the requests for those blocks. So here for the first 3, this was not in memory. This was not in memory. This is not in memory. This is not in memory. And then, damn it, this one's no longer in memory, and this one's no longer in memory. So I'm constantly going out to the mass storage device and reading into main memory. So that's also a form of thrashing, Jordan. Okay. Okay. Does that answer your question? Good. All right. Next question, please.
On file systems, I'm still not completely 100% on the original Unix file system that we were talking about, and optimization on that.
Okay, so we did not finish our discussion of file systems. It won't be on the exam.
Okay.
But do you have a question that I can just sort of answer quickly, knowing that we'll get back to it after the exam?
I'm still a little confused about, like, when we're talking about the owner, the group, and everyone else.
Okay. Let me demonstrate. Do I have a terminal running? Good. I have a Linux one and not a Mac one. All right, so let me show you that. Okay, so where am I? It doesn't matter, but okay, let's take a look at the current directory that I'm in. So ls minus l of period dot. Okay, ls minus la dot. Okay, so there are two files in this directory, a.out and main.s. However, the contents of the directory always has its first entry corresponding to itself. That's dot. The second entry of a directory is always a reference to this directory's parent. So dot and dot dot, they don't explicitly name a directory, they implicitly name directories. Dot means the directory you're in, and dot dot means your parent. Remember, it's a hierarchical file system. So like nodes in a tree, everybody's got a parent except for the root node. So now looking at the permission bits, in what you see here, there are 10 digits of permissions. 9 of them are actual permissions, and then one column is not permissions, but more status. So looking here, the first column is that status bit. It's giving you some information about what the file is. In this case, dot and dot dot have the letter D, which stands for directory. And then in every case, you have 9 more digits. And these digits correspond to the permissions that the owner, the owner's, the group, and then everyone else. Everyone else. Okay, so the owner, that's pretty clear. The owner is either the person that created the file or perhaps the someone else. And because I can change the ownership of files, let me switch back and demonstrate that. See, I'm thrashing. Okay, so here is the owner of the file. And here is the name of the group associated with the file. So cat slash EBC slash, all right, group. Okay, so these are the groups that are available on the system, this particular system. And the way that you read that is the CD-ROM group or the floppy group. That group number of CD-ROM is 24, and the members of the group are only the account USER. Okay, so think of it this way. Suppose you have a file that you only want yourself to have access to. You, as the owner, have access to a file. So let's see, change mod to 600 of main.s. Okay, so 6 in octal is 110. So here's read, write, execute, 110. Now, if I wanted to, so that's a file that you want to keep to yourself. But let's say you want to share that for people who are in the payroll department. Suppose there's a group named payroll, then you could add permission bits that allow you and anyone who's a member of the payroll group to access the file. So chmod 660 main.s. And now I have read-write permission for myself and read-write permission for everyone in the owner of the group. I would also have to, here, I'll show you. CHGRP, change group, to the, I saw one a moment ago, the CD-ROM group of main.s. Now let's look again. So Rebecca, now you see that the name of the group CD-ROM is the group that main.s belongs to. So anyone in the CD-ROM group has the permissions indicated in that second set of 3 digits.
So how can you, like right now, you can't access, or so like right now, are you able to access that file?
I am.
Okay.
Because I am, my account is user. So you can say, who am I? I'm user. So because I am user, these 3 bits take precedence. So I have access to this file. Okay,
Now,
go ahead.
So if you, for some reason, changed it to one of the groups that you mentioned above that doesn't have user as a member, you would not be able to access it?
Well, if the owner's bits still allow me access, and I am the owner, that takes precedence over the group. So the order of the checking is owner, group, everyone else. So I don't know, let's find out what happens if I say chmod 0 of main.s. Oh, gee, let me do it. Now let's take a look at main.s. Nobody's got permissions, so what's inside main.s? I don't know. I can't get there anymore. Okay, no problem. I'll change the mode back. Change mode 644 main.s. Oh, okay. Well, I can get it back to it now.
Why didn't it require you to sudo to undo it?
I was kind of expecting it to require it, but so the answer to your question is why? Is because it did. Personally, between you and me, I was expecting to have to become the super user to change the position, change the permission bits back.
Which this doesn't actually have sudo installed.
This does? Yes, it does. Well, it has SU.
Oh, that's not sudo.
Okay.
Well, but yeah, I guess you're just changing into root.
Yeah. So SU stands for substitute user. And sudo is really sudo, but nobody pronounces it that way. So it's substitute a user and do something.
I didn't actually know that.
Mm-hmm. Okay, but back to the permission bits. So you got read, write, execute for user, the owner, the group, and the everyone else. Now, execute is going to be true for anything that you care to execute. So /a.out, I don't even know what program this is. Okay. But now I'm going to change the mode of the file, chmod it, and I'm going to make it 444 ./a.out. Let's look at the mode. Now it's only read permission for a.out. Let me try executing it again. I can't. Let's put it back, 755. And it's back to executable. Notice even the highlighting color changed when it wasn't executable. It's green when it was executable and not green when it wasn't.
What would happen if you made main.s executable?
That's an interesting question. And I would
yell at
love,
you.
I would love to digress into that. So here we go. Chmod 755 main.s. And oh boy, they're both in green. I must be able to execute it. /main.s. Nope. It tried. It didn't make any sense.
Does it like try to read it as if it's machine code, but
No, it's shell.
code. Yeah, that makes sense.
Mm-hmm. Mm-hmm. So let me try this. vi foo, and I'm going to say pwd echo comp org is the best class ever. Okay, which is true. All right, now /foo, permission denied. Okay, chmod 755 foo, /foo. And now it's executed as a shell script.
By the way, I believe this is true on Linux. You can do plus X or plus some other, and
Correct.
you'll add to the permission bit instead of having to set them all.
That is correct. CFS is correct. There are different syntaxes that one may employ using chmod.
And I've had to use the plus X thing because Apple is dumb, and when they updated to Catalina or something, certain executables, the executable bit was like removed. So when you try to launch the program, it just didn't do anything. And then you have to go into the file and change the permissions to X. It's kind of annoying.
Yeah, well, Apple and annoying both are synonyms.
Didn't Catalina also get rid of all 32-bit programs?
Either Catalina or Big Sur.
Okay.
Yeah, and
I think Big Sur officially did away with it. Catalina was a warning.
Yeah.
I
Now,
think.
it's funny because I can take a program, an executable from the middle 1980s on Windows and run it without problem. But I can take an executable that I made last week on the Mac and I can't run it today because Apple.
In their defense, it allows their OS to be a bit leaner than Windows since they don't have to support code from a gajillion and a half years ago.
Oh, you're absolutely right. Right. So instead of the Mac OS taking 60 gigabytes for an empty, it might have only taken 59. You're absolutely right.
I don't support Apple in this. I'm just saying it does have its advantages of not supporting every single legacy code ever, like Windows does.
Let me put it back to you this way. So Windows, their emphasis is on getting work done and working your way. Apple emphasis is you working our way. So you're the user.
True.
Go screw yourself.
It's completely true.
There.
But
Right.
Apple with round buttons.
Okay. Oh, but her emails. Okay. So what is next? Another question.
Yes, I have a good question.
Yeah.
So hexadecimals.
Mhm.
If the hexadecimal is 0x8f, is that like that would be 8/16 plus f, which is 15, right?
No. Let's back up. What are we talking about? Are we talking about an integer, floating point? What?
I'm just so I guess the big question is like, do I read from the right to the left or the left to the right?
You read normally, so left to right. Let's go here. So 8f is 100. Sorry, 1111. So here's 8, and here's f. And it doesn't matter on a given machine. 8f will always correspond to this value, whether it's big endian or little endian. You let the hardware interpret it. If you say 8f, what you mean is 10001111. Whether it's big endian or a little endian, not Indian. It's the best I could do. All right, now something that I should add with the permission bits is the following. Let's take a look at the permission bits of the directories. Does this cause anyone to want to ask a question?
What are those numbers to the left of user represent?
Oh, I'll be happy to answer that in a moment. But what I'm wondering is, can you really execute a directory? So for directories, the execute bit does not mean execution. It means, can you search it? Can you pass through it? So for instance, I'm going to make a directory called bar. And let's look at the permission bits of bar. So it's a directory, and it's read, write, execute, read, execute, read, execute. And what the hell can you execute a directory for? Well, I don't know. Let's take a look. Let's create something in bar. All right, let's look at what's in bar. Okay, now there's a file called bar. Chmod 666 bar. No big deal. Okay, now let's take a look at what's in bar. Uh-oh. So for directories, the execute bit is repurposed for, can you traverse this directory? Okay. So let's get this back. Chmod 455 bar. And now can we see that? Oh, still can't. Let's see, what did I make the permissions? Oh, I don't have permission to see what's in the directory. So let's make that 555. And now I can cat bar, bar, bar. Okay. Now, again about permission bits, because you got me on a roll here. Let's take a look at another type of file. I was about to say a special file, but then I realized that's actually the name of this type of file, special files. So let's just do an ls. Ooh, lots of ugly colors there. So ls minus L of tty star. And yet another letter here. So not a D, it's a C. It means that this is a character special file, which means that access to, that it corresponds to a device, and that it access to the device is available one character at a time. As opposed to, all right, let's go into disk. And these are directories. Let's go to by path. Hello. By path. I thought it was a directory.
A hyphen, not an underscore.
Oh, got it. Thank you. Okay, so these are just links. Oh, well. So, but I see where they're linking to, so that's where I'll go. So L says this is a linked file. It's not a file itself, it's a link to a file. And now let's go up to VDA2. All right. CD to, did it say VD? Okay.
Can't you CD to the symlink or whatever type of link it is? And it should go to the actual directory?
Yeah, it could have, but I didn't think of doing that. So here's another letter, B. This is a block special file, which means it corresponds to a device, and access to this device is by block at a time. This could be painful, but I expect it to fail. Good. Would you like to see the bits in my the bits on my file? I can then say sudo odvda1. Oh yeah, su. Forgot what system I'm on. Now where am I? Yeah, I'm still in dev. odvda1. Okay, so those are the bits on my hard drive. This will go on for a long time.
Very usable and human readable.
What format are those numbers in? They're not binary. Is that a hexadecimal? Or octal?
Do you see any Fs?
I do not. That was why. Is it octal?
Yeah, and that's why it begins with OV. Octal dump.
Now, if you did HD, would that be high definition?
No, that's terrible, George. Okay, so
terrible job.
man OD. All right. So we could, oh, you can modify your hard drive. Let's see. -X. All right, so OD-X. There, now it's in hexadecimal.
Now, if you did BD, would it be binary?
Nope,
No.
nobody's interested in binary.
I like doing it to show it off to my friends and act like I know what it's saying.
Well, I used to have to, you joke about that, but I have many times edited a raw hard drive using a tool like this.
I'm so sorry.
What's to be sorry about? In fact, when I would have done it most recently would be in creating the Cephas's favorite OS project, which was a file system debugger, file system checker. So I would go into a raw file system and modify bits to cause errors that his program would have to find. And so will you next term for many of you.
Are you teaching OS next semester?
I'm sorry, what's
Are you
that?
teaching OS next semester?
I am the only one, and I think this is fair to say, who has the stomach to teach both CompOrg and OS.
Isn't pretty much everybody else quite a bit higher level in general?
Yes, in general. Yeah. So I admit it. I'm just a low level kind of guy.
I love how low level means a lot more work rather than high level being less work.
Mm-hmm.
He's just chilling in his mother's basement.
Yeah, I am. Okay, questions?
So this is kind of off topic. Do we know what courses are being offered next semester?
Yeah, aren't they available to you by now?
I don't think so. Not for the fall.
You can check the ones for the spring semester. Not spring, the J term.
Yeah.
Yeah,
Right.
to sign up for J term. I'm talking about fall.
Okay. Well, because your faithful instructor is the chair of the department, I can show you the schedule for next year. Shall we?
We shall.
Where am I? Okay. Let's see. Anytime you're ready. So for fall of next year, you have these choices. So I would imagine that many of you who are becoming seniors next year must be in this class and must be in that class.
OS isn't required though, correct?
I think it is because it's a writing intensive class and you need one to graduate.
I thought
no, OS is not writing intensive. It's work intensive. But yeah, depending upon your year, OS is required.
that makes sense.
Okay, if you want to look at spring 2022, these are your choices. This will be Game Development 2, 2720, brand new. And this will be, I forget the number, this will be Software Security. So these two are just placeholders for now.
Man, that's a high level class there.
Yeah. So they're just placeholders.
Ever need.
Okay. And for J term of next year, this is what you've got. This will be, I expect this will be game development 3. Okay. By the way, the game development minor and the concentration is now approved. It goes to the board of directors today or tomorrow, and after that, it's official. So
if that would be game development 3, then does that mean that it's going to be a May term again? Because if it's in January, then it would mean 1 is in the fall, 3 is in January, and 2 is the rest of the semester?
Correct. You got me.
I think Bingen did tell us that that's going to be like it is going to be like more of a topics course in game development.
Mm-hmm. Yeah.
I forget exactly what he has planned for that, but it's
okay. So Gabe, you're right. I forgot. Who knows? I'm not making a commitment for the campus though. So you're right. I forgot that J stands for January. Okay. Okay. Back to questions that might actually impact your exam.
Can you go over like the structure of the exam? I know you did once before, but could you do it again, please?
Okay. The exam will be largely multiple choice. I might, while I've been talking to you right now, it occurs to me that I would like to put in some short answers. So for example, short answer might be, what's your favorite ARM instruction and why? That seems like a reasonable question. So multiple choice would be, multiple choice, like suppose the following conditions, which of the below instructions does the perform some desired outcome? So Jacob, are you driving in England? If so, you're driving.
No, I'm in the passenger seat.
It's remarkably good via the telephone. You haven't been, as Thomas would say, you haven't been fax machining. It's remarkably good.
Honestly, it's better than Carthage's Wi-Fi.
Okay.
That's not accurate.
It's more reliable than Carthage's internet, I'll say that.
Yeah.
Not convinced that's accurate either.
I'll fight you for the fact.
Mm-hmm.
What?
So, question, and we don't have to do it because, whatever, but could you give us a like a practice problem for us to write some assembly code that we can go over?
You mean like what, here and now?
Just so we can kind of, if we have questions,
okay.
It's better in my head.
Well, here's a practice problem that I've seen on Reddit. Write Minecraft, except everyone is in the shape, all of the blocks are in the shape of tomatoes.
All right.
I mean, Jordan, I don't know how to answer that.
No, good point. It sounded better in my head.
That would be an extraordinarily annoying thing to do in assembly.
Yeah.
You'd have to write your own graphics API. Ew. Well, I guess you can use libraries. It'd just be ugly. Writing Vulkan and or OpenGL using assembly does not sound fun. It was annoying with what's it called? JavaScript?
Okay, questions? All right, you started off really well. You had some good questions there. Let's keep the ball.
Yeah, so on the GitHub thing for progress, February 4th, we talked about not a number in infinity. Can we quickly go over that, how that's shown in assembly?
Sure. Okay. So, so floating point numbers, we'll look at single precision, but it's the same. This part is the same for double precision. So you've got the sign, which is 1 bit, and it is the sign bit. Then you have 8 bits. Then you have 8 bits of exponent. And then you have, what was it, 43 bits? 43, 44, 8. No, we're talking about 32-bit, 23 bits. So 23 and 1 is 24, plus 8 is 32. And this is the fraction. Okay, so there are 2 values of exponent that are reserved. And those would be out of the 8 bits, that would be FF. So let's see, 4 bits, 8 bits. Okay, FF and 00. So these 2 values in the exponent are reserved. And FF, if I remember correctly, I may be getting these backwards, is going to be infinity. And this one is, I believe, is going to be not a number. Okay. And we can see them in that program that I wrote, that lovely, lovely program, which I'm not prepared to demonstrate. But if you remember the second version of the floating point program, I built in magic numbers. If you entered -100, it would do an operation that would cause infinity. And if you did -200, it would do an operation that would cause not a number. Like dividing by 0 would be infinity, and square root of -1 would be not a number. Okay, Jordan, does that answer your question?
Not a real number anyway.
Aha. I got that. More questions?
Can we on the 4th we also talked about memory mapped IO. Could we review that real quick?
Okay. So memory mapped IO. Okay, so in the beginning, let's take the earliest Intel microprocessors, for example. They had special instructions to read and write hardware devices. And that was like the in instruction and the out instruction. And it would be in on some number and out on some number. And the number would be vary whether or not it's a serial port or parallel port or the storage device or the keyboard, etc. But these numbers didn't correspond. They corresponded to some special mapping. But later on, people said, you know, it doesn't really make sense to have separate instructions to do input and output from devices. Why not just map the device registers into ordinary memory? And then we don't need these special instructions. We could use the ordinary access, read from memory, write to memory instructions. So in the address space, in the physical address space, there are some regions which are reserved for various purposes, including to this area, which I'm probably not drawing in the right place. I have no idea where that region is. Maybe it's high memory, maybe it's low memory. It's just not on my radar. Would be reserved for the device control registers. Now, the word register, don't be confused. That doesn't mean it's a CPU register. It means that it is a something like a CPU register, only it exists on another piece of hardware. And that's essentially it. And notice I was careful to say in physical memory, because hardware device registers, simply not safe to put them into the address space of your program. So that's a part of physical memory you can't get to. Okay?
Is this still the generally preferred method instead of like serial communication or something?
Well, question number one is yes, this is still the preferred method. Question number two, for like serial, it really doesn't matter. You know, you can, let's say it was a serial device that you were talking to, you could write 8 or 16 or 32 bits to it all at once. That write is like in parallel. And then the hardware that stands behind that location in physical memory, that would do the translation from the 8 or 16 or 32 bits into a serial communication. If you've ever worked with like the Arduino, you've experienced things like reading or writing to a location causes serial communication to take place.
So wait, is serial communication a form of memory map, Aya?
No, what I mean by serial is the bits go out one at a time.
Yeah, that's what I mean. But
Yeah,
it is
so,
like a direct communication. I send thing, I wait for device, device send
yeah.
thing back.
So, for example, let's take a device that has 3 registers. Or tell you what, let's make a device that has 2 registers, and we'll show you how you can do double duty. On this fictitious device, you have 1 register, which is the control register, and 1 register, which is the data register. So you can read or write to the control register, and you could read or write to the data register. So for instance, you might write to the data register and put a H, capital H into the data register, and then write a value that had one of the bits, which was the W, the write bit. It says if you turn that bit to a 1, whatever's in the data register is sent to the device. That's a reasonable, simple example. So if you read from the data register after having set the, let's say, the read bit, then you get something back. So when you're, the moral of the story is, though, as a detail, when you're dealing with hardware registers, reading from them may actually have a different bit layout than writing to them. So that's neither here nor there. By the way, one of the most fun things I've ever done in coding was writing drivers, the software necessary to control hardware. That is a lot of fun to do, and here's why. Ordinarily, you know, we get all excited if you write some code and the right number pops out, right? But when you're working on device drivers, it's a lot more fun because if you write your code correctly, the railgun fires around and it destroys a spaceship. So device drivers are way more fun than ordinary software. I think Cephas is still thrashing. So what I just said is in all seriousness, in that when you're writing device drivers, it is a lot of fun to write code and then see something move in the real world, or lights change in the real world, you know, or the railgun fires. There is a Reddit for people who create their own railguns. Pretty cool.
There's a Reddit for pretty much everything.
Yeah, including the things you can't think of. So it's not even sufficient to say there's a Reddit for everything you can think of. Forget about that. There's everything you can't think of, don't want to think of. And if you thought of those things, you'd have to go to confession. So, but there's a Reddit for it.
It's like rule 39, rule something something. I don't remember what it is.
I'm not familiar with what you're referring to.
I bet Jordan knows. Jordan knows everything.
Yeah, he is our expert at pop culture.
Yeah.
You know, is
I know
it
what
rule
you're talking
39?
about. I don't want to talk about it. We don't talk about that side of the internet.
Okay, other questions? I'll tell you some insanely good news. And it's not that I saved 15% on my car insurance. So I have this new M1, and I've helped some of you while running on the Mac M1. And for example, I remember Cephas saying, "Oh my God, that's slow." And it is. It was horribly slow because running the virtual machine that you run. But Parallels, the company that makes the virtual machine software for Macintosh, yesterday introduced a new test version of Parallels Desktop, which allows you to run ARM-based Linux distros in the virtual machine. So I fired it up, loaded Ubuntu for ARM, and it is blindingly fast. So I'm very happy about that. I mean, it's blindingly fast. So that's really cool. That's good news. All right, if there's no more questions, we can call it a day. All right, I'll see you on Tuesday. The exam will take place via Schoology. Okay. And I will be here in the classroom during the normal time in case you have questions about the questions. Okay? But otherwise, attendance is optional. The exam will end at the appointed time for the ending of class, 2:10. Okay, see you around.